Let's explore the process of sizing the main service disconnect, distribution panel, and feeders for a portable classroom building. Firstly, we need to determine the total load current. There are 11 sections with 125 amps load centers, which totals 11 multiplied by 125 amps, equaling 1375 amps. Then there are 2 sections with 150 amps load centers, totaling 2 multiplied by 150 amps, equaling 300 amps. The grand total of the load current is 1375 amps plus 300 amps, equaling 1675 amps. Secondly, we need to apply a demand factor for the heating, ventilation, and air conditioning units, as per the National Electrical Code Table 430.24. Let's use the demand factor of 0.75. The peak demand is calculated by multiplying the total load current of 1675 amps by the demand factor of 0.75, which equals 1256.25 amps. Then you round up to the nearest standard breaker size, which would be 1400 amps for the main service disconnect switch. Next, let's discuss the distribution panel. The total branch circuit load is the same as the total load current, which is 1675 amps. However, the distribution panel must also handle the feeder current from the service disconnect switch. Therefore, the distribution panel must be rated for at least 1400 amps plus 1675 amps, equaling 3075 amps. Now, let's move on to feeder sizing, starting with the feeder to the distribution panel. The current is 1400 amps, based on the main service disconnect switch rating. The voltage is 208/120 Y volts. For the conductor size, use a 4/0 American wire gauge copper conductor with a 75 degrees Celsius insulation temperature rating. Finally, let's look at the feeders to the load centers. For the 125 amps load centers, the current is 125 amps. Use a 1/0 American wire gauge copper conductor with a 75 degrees Celsius insulation temperature rating. For the 150 amps load centers, the current is 150 amps. Use a 3/0 American wire gauge copper conductor with a 75 degrees Celsius insulation temperature rating. To summarize, you will need a 1400 amps main service disconnect switch, a 3075 amps distribution panel, a 4/0 American wire gauge copper feeder with 75 degrees Celsius insulation to the distribution panel, a 1/0 American wire gauge copper feeder with 75 degrees Celsius insulation to the 125 amps load centers, and a 3/0 American wire gauge copper feeder with 75 degrees Celsius insulation to the 150 amps load centers. To delve deeper into the calculations and requirements, let's elaborate on each component. Starting with the main service disconnect switch. This switch is the primary point of disconnecting power to the entire portable classroom building. Its size is determined by the total calculated load, adjusted by any applicable demand factors. We arrived at 1400 amps by totaling the individual load center amperages, applying a demand factor for the HVAC units, and then rounding up to the next standard breaker size. The demand factor accounts for the likelihood that not all HVAC units will operate at the maximum load simultaneously. Without this, the service size would be significantly larger and potentially wasteful. For the distribution panel, it serves as a central hub for distributing power to the individual load centers within each classroom section. Its amperage rating must exceed the sum of all feeder currents plus the main service feeder current. This ensures that the panel can safely handle the entire building's electrical demand. The 3075 amps rating might seem substantial, but it is crucial for accommodating future load growth and providing a safety margin. Regarding feeder sizing, feeders are the conductors that carry power from the main service disconnect to the distribution panel and then to each individual load center. Their size is determined by the amount of current they are expected to carry continuously. The National Electrical Code specifies ampacity ratings for different conductor sizes and insulation types. For the feeder to the distribution panel, we selected 4/0 American wire gauge copper conductors with 75 degrees Celsius insulation because they can safely carry 1400 amps at the specified voltage. Similarly, the feeders to the 125 amps and 150 amps load centers are sized based on their respective current demands. Choosing the correct conductor size is essential to prevent overheating, voltage drop, and potential fire hazards. Using copper conductors is a common practice due to their excellent conductivity and corrosion resistance, although aluminum conductors are an alternative with different ampacity ratings. The 75 degrees Celsius insulation rating is a standard choice that allows conductors to operate safely at higher temperatures. Let's explore the NEC tables in more detail. NEC Table 310.15b16 provides ampacity ratings for conductors based on insulation type and installation conditions. Consulting this table is critical for selecting the appropriate conductor size for each feeder. Additionally, NEC Table 430.24 outlines demand factors for motor loads, which are relevant for the HVAC units in the classroom sections. These demand factors allow for reducing the overall service size by accounting for the intermittent operation of motors. It's also important to consider voltage drop when sizing feeders. Excessive voltage drop can lead to poor equipment performance and reduced efficiency. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall. To minimize voltage drop, larger conductor sizes may be necessary, especially for longer feeder runs. Grounding and bonding are also essential aspects of the electrical system. A proper grounding system provides a low impedance path for fault currents, helping to protect against electrical shock and equipment damage. Grounding electrodes, such as ground rods or metal water pipes, are connected to the service equipment and the building's metal structure. Bonding ensures that all metal parts of the electrical system are electrically connected, creating a common ground potential. Overcurrent protection is another critical element. Circuit breakers and fuses are used to protect conductors and equipment from overloads and short circuits. The size of the overcurrent protection device should be matched to the ampacity of the conductor it is protecting. Coordinating overcurrent protection devices is important to ensure that only the faulted circuit is interrupted, minimizing disruption to the rest of the system. In addition to the NEC, local electrical codes and regulations may impose additional requirements. It's important to consult with local authorities to ensure compliance with all applicable codes. Proper documentation is essential for any electrical installation. Detailed plans, calculations, and specifications should be prepared and submitted for approval before commencing work. A thorough inspection should be performed after the installation is complete to verify compliance with codes and standards. Ongoing maintenance is crucial for ensuring the continued safe and reliable operation of the electrical system. Regular inspections, testing, and cleaning should be performed to identify and address any potential problems. Thermographic scanning can be used to detect hotspots in electrical connections, indicating loose or corroded connections. Furthermore, consider future expansion when designing the electrical system. Adding spare capacity to the service and distribution panel can make it easier to accommodate future load growth. Using conduit for wiring allows for easy replacement or addition of conductors as needed. Remember that electrical work should only be performed by qualified and licensed electricians. Working with electricity can be dangerous, and improper installation or maintenance can lead to serious injury or property damage. Safety should always be the top priority. In conclusion, sizing the electrical service for a portable classroom building requires careful consideration of load calculations, demand factors, conductor sizing, and code compliance. By following the steps outlined above and consulting with qualified professionals, you can ensure a safe and efficient electrical system that meets the needs of the building. Remember to prioritize safety and comply with all applicable codes and regulations. Don't forget to account for future expansion and provide adequate grounding and overcurrent protection. These best practices will ensure long-term reliability and safety. When planning for electrical services in a portable classroom building, consider energy efficiency. High-efficiency lighting, appliances, and HVAC systems can significantly reduce energy consumption and operating costs. LED lighting, for example, uses considerably less energy than traditional incandescent or fluorescent lighting. Programmable thermostats and energy-efficient HVAC units can also help to minimize energy waste. Conducting an energy audit can identify areas where energy savings can be achieved. In addition to energy efficiency, consider renewable energy sources. Solar panels can be installed on the roof of the portable classroom building to generate electricity. Wind turbines can also be used in areas with sufficient wind resources. Renewable energy sources can reduce reliance on the grid and lower carbon emissions. Battery storage systems can store excess energy generated by renewable sources for later use. This can improve the reliability of the electrical system and reduce peak demand charges. Smart grid technologies can also be incorporated into the electrical system. Smart meters provide real-time data on energy consumption, allowing occupants to monitor their energy usage and identify opportunities for savings. Smart appliances and devices can be programmed to automatically adjust their energy consumption based on grid conditions. Building automation systems can integrate and control various building systems such as lighting, HVAC, and security. This can optimize energy efficiency and improve occupant comfort. When selecting electrical equipment, choose products that are certified by reputable organizations such as Underwriters Laboratories or the Canadian Standards Association. These certifications ensure that the equipment meets safety and performance standards. Also, consider the environmental impact of electrical equipment. Choose products that are made from sustainable materials and are recyclable. Dispose of old electrical equipment properly to prevent pollution. Education and awareness are important for promoting energy conservation. Provide occupants with information on how to reduce energy consumption and use electrical equipment safely. Encourage them to turn off lights and appliances when not in use. Post signs and labels to remind occupants of energy-saving tips. Partner with local utilities and energy efficiency organizations to offer training and resources. By implementing these strategies, you can create a more sustainable and energy-efficient portable classroom building. This will not only reduce operating costs but also contribute to a healthier environment. Remember to consult with qualified professionals to ensure that all energy efficiency measures are properly implemented and comply with applicable codes and regulations. Consider the specific needs and characteristics of the portable classroom building when planning the electrical system. The building's size, layout, occupancy, and climate will all affect the electrical requirements. A thorough assessment of these factors is essential for designing an appropriate and efficient electrical system. When planning the layout of the electrical system, consider accessibility for maintenance and repairs. Locate electrical panels and equipment in easily accessible areas. Provide sufficient clearance around equipment for safe working conditions. Label all electrical circuits and components clearly. Keep accurate records of the electrical system, including plans, specifications, and maintenance logs. This will facilitate future maintenance and troubleshooting. Conduct regular inspections of the electrical system to identify and address any potential problems. Look for signs of damage, overheating, or corrosion. Test the operation of circuit breakers and ground fault circuit interrupters. Repair or replace any defective components promptly. Keep the electrical system clean and free of debris. Dust and dirt can accumulate on electrical equipment and cause overheating. Clean electrical equipment regularly with a vacuum cleaner or a soft cloth. Avoid using water or other liquids to clean electrical equipment, as this can create a shock hazard. Protect the electrical system from moisture and water damage. Install waterproof covers on outdoor electrical outlets and equipment. Seal any openings in the building envelope to prevent water intrusion. Consider the impact of electromagnetic interference on sensitive electronic equipment. Shielded cables and filters can be used to reduce interference. Locate sensitive equipment away from sources of electromagnetic radiation such as transformers and motors. Use surge protectors to protect electronic equipment from voltage spikes. Lightning protection systems can also be installed to protect the building from lightning strikes. When planning the electrical system, consider the needs of people with disabilities. Provide accessible electrical outlets and switches. Ensure that electrical equipment is located within reach of people in wheelchairs. Use tactile markings on electrical controls to assist people with visual impairments. Comply with the Americans with Disabilities Act and other applicable accessibility standards. Remember that the electrical system is an integral part of the portable classroom building. Proper planning, installation, and maintenance are essential for ensuring safety, reliability, and efficiency. Consult with qualified professionals to ensure that the electrical system meets the needs of the building and complies with all applicable codes and regulations. Stay up to date on the latest electrical technologies and best practices. This will enable you to make informed decisions about the electrical system and ensure that it remains safe and efficient for years to come. Finally, consider the life cycle cost of the electrical system. Choose durable and reliable equipment that will minimize maintenance and replacement costs over the long term. Invest in energy-efficient technologies that will reduce operating costs. By taking a long-term perspective, you can create an electrical system that provides excellent value for money.